Scattering parameters, directional coupler, series on microwave engineering, lecture number 2.16. S parameters or S matrix. These are meant for characterizing or modeling a microwave circuit or a microwave junction. The modeling with S parameters in general involves following certain procedural steps. In the present session, we consider directional coupler, a 4-port microwave junction, to obtain its S matrix duly following the standard procedural steps that are almost standard. Let us move into the course session where scattering matrix, S matrix for directional coupler is derived, where the procedure that is followed in deriving S matrix for a linear microwave circuit is illustrated clearly. Here are certain introductory statements or sentences. For an ideal directional coupler, ideal means lossless, reciprocal, with infinite directivity, which implies perfect isolation between input port and decoupled port. The scattering matrix appears as S is 0, 0, P, J, Q, 0, 0, J, Q, P, P, J, Q, 0, 0, J, Q, P, 0, 0. So the matrix is in terms of two quantities, P and Q. What are these P and Q quantities? Here P is square root of the ratio PC to Pi. P and Q are related through P square plus Q square equal to 1. Or one can say Q is square root of 1 minus P square. P is square root of PC by Pi, where PC is power delivered to the matched load at the coupled port, and Pi is the power entering into the coupler under matched termination at other ports. Directional coupler is a 4-port device. Each port has its own name and significance too. The port where source is connected, that port is called input port. Port which is opposite to input port is called output port or through port. Output port can also be defined as the port where majority of the input appears. Major portion of the input wave appears. The port which is by the side of the input port is decoupled port. The remaining port is called coupled port. Coupled port can also be defined as the port where the diverted wave or the sampled wave appears. Decoupled port is one which has perfect isolation from input port. With these few words regarding ports and their significance, now let us move to derive the S matrix of an ideal directional coupler. Finding the S matrix of a device is a multi-step process involving modeling of its physics. The first step always is sketching the device with proper port designation. Notice scattering matrix of a device, it depends upon the port numbering. If there is a change in port numbering, scattering matrix also changes automatically. So S matrix always is in reference to a particular port numbering. This is the case for any device. The device can be E plenty, it can be H plenty, it can be a directional coupler, it can be magic T. Irrespective of the device, S matrix is dependent upon port numbering. The starting point is considering a directional coupler with certain port numbering. Consider directional coupler with the port designations as shown below. 1, 2, 3, 4. Notice here anti-clockwise numbering. scheme is followed. Usually, 1 is given to input port. Port below input port is decoupled port. Port opposite to input port is through port or output port. Remaining port is coupled. We refer to this port numbering several times in the process. In the procedure we follow in the derivation of the matrix. Let us start the actual process. The directional coupler is a 4-port junction and hence its matrix must be a 4 by 4 square 1. Let it be S11, S12, S13, S14, S21, S22, S23, S24, S31, S32, S33, S34, S41, S42, S43, S. In the directional coupler, all the ports 1, 2, 3, 4, they are perfectly matched to the junction. It implies S11 equal to S22 equal to S33 equal to S44 equal to 0. Also, the ports 1 and 2 are perfectly isolated from each other, as are the ports 3 and 4. Hence, parameters S12 equal to S21 equal to S34 equal to S43 equal to 0. 1 is input port, 2 is decoupled port. Therefore, there exists isolation. This isolation is perfect when the device is an ideal one. Port 3 is coupled port, port 4 is output port. There exists isolation between these two, and it is perfect when the device is an ideal one. Hence, this relation S12, S21, S34, S43 all are zeros. If the isolation is not perfect, these parameters would have assumed non-zero values. Incorporating these two aspects, the S matrix of the ideal device becomes 0, 0, S13, S14. 0, 0, S23, S24, S31, S32, 0, 0, S41, S42, 0, 0. As the coupler is an ideal one, it is reciprocal and hence the matrix must be symmetrical. It implies Sij is equal to Sji for I not equal to j. Hence the S matrix becomes 0, 0, S13, S14, 0, 0, S23, S24, S13, S23, 0, 0, S14, S24, 0, 0. When we started the process of derivation, number of unknowns are 4 into 4, 16. After a few steps, right now, you can find the number of unknowns as 4. Next, in ideal directional coupler, the coupling between ports 1 and 3 is the same as that between 2 and 4, making S13 equal to S24. Similarly, the coupling between ports 1 and 4 is the same as that between 2 and 3, making S14 equal to S23. After including these aspects, the matrix becomes 0, 0, S13, S14, 0, 0, S14, S13, S13, S14, 0, 0, S14, S13, 0, 0. Number of unknowns still got reduced. Now they are much more fewer than in earlier version of the matrix. As the junction is ideal, it must be lossless and its S matrix must be a unitary one, obeying unit property and also zero property. Applying zero property to row 1 and row 2, it can be obtained that S13 into S14 conjugate plus S14 into S13 conjugate equal to 0. Now, if S13 is a real quantity, let us say P, then the above equation becomes P into S14 conjugate plus S14 equal to 0. To satisfy this equation, the quotient S14 must be pure imaginary. You see, in this equation, P is not 0. So the second factor must be 0. When it can be 0? Only when S14 is pure imaginary. And let it be JQ. Incorporating these aspects, the matrix becomes 0, 0, P, JQ, 0, 0, JQ, P. P JQ00, JQP00. You can notice this is the matrix that was shown, that was given as S matrix of directional coupler at the beginning of the session. Here one can assume that S14 as a real quantity, and in that case S13 becomes imaginary, carrying a J with it. So another possibility is also there. That possibility is explaining. In any case, a J appears with one of the outputs, indicating the fact that outputs of the coupler exhibit quadrature phase difference. Quadrature means 90 degrees. Therefore, there exists a 90 degrees difference between the outputs of directional coupler. Further reduction of this matrix is possible if the coupling C in dB of the directional coupler is given. This parameter C is usually available as it is given by the manufacturer along with the directional coupler. Further reduction of this matrix can be done by establishing a connection between P and C. That connection is P is equal to antilog minus C by 20. Once P value is found, Q value can be ascertained from the equation P square plus Q square equal to 1. So to give numerical values to elements of the S matrix pertaining to directional coupler, coupling factor is required. Of course, it is commonly available. So one can give matrix of the directional coupler completely and totally. This is all what I want to share with you for right now. To recap, the S matrix of an ideal directional coupler, it is derived various standard procedural steps that are universally followed in modeling a device with S parameters. They are all followed scrupulously in the derivation process. Hence, this session illustrates the methodology followed in modeling circuits with S parameters. Hope you have a beautiful, wonderful, fruitful, successful, enriching, and also enchanting learning experience. Enough for now. See you soon again. Bye bye.